Hello. So based on first principles, we've now taken LTI systems and shown that you can represent them using impulse responses. And we've also introduced infinite impulse response systems, which can be implemented using difference equations. We can also implement an IIR system, and I put can in quotes here, using the impulse response and the convolution equation. It's just that since the impulse response is infinite in length, that becomes impractical very quickly. However, in order for it to be stable, we know that the impulse response of an infinite impulse response system must be absolutely summable, which means that it must eventually go to zero. And so it's not uncommon to have some system that has an infinite impulse response where it's implemented as a truncated impulse response. We're not going to spend too much time with that. Now we're going to work on frequency responses. So let's review a basic concept of linear algebra, but we're going to put a different twist on it, if you will. In linear algebra, you learn about the concept of eigenvalues and eigenvectors. Well, here's a new one, perhaps. X of n is an eigenfunction of a system. It could also be viewed, in this case, as an eigenvalue or eigenvector, because especially if it consists of discrete values. But since in general it could be infinite in length, it's easier to just talk about it as an eigenfunction of a system. So when we talk about eigenvalues in linear algebra, you have a matrix multiplying a vector, and you get the same vector back, but it's been scaled by some eigenvalue. In this case, here we have an eigenvalue, and it could be complex, and it is unique to each eigenfunction. Just as different eigenvectors may have different eigenvalues, so we also have that different eigenfunctions may have different eigenvalues. Okay, so here's a little prefiguring of what's to come. For LTI systems, your eigenfunctions are all of the form j omega naught n. And what we get out is h e raised j omega naught times e j omega naught n. So we have our eigenfunction, and this is our eigenvalue. Now it looks like a function here the way I've written it, and in a sense it is. It's a function of omega naught, okay, but just as the eigenfunction is too. So we're essentially parameterizing the eigenvalue to associate it with the eigenfunction. So let's go through how we actually do this. Where does this come from? So we'll suppose that x of n is equal to e j omega n. And we have some system, and since any linear time invariant system can be represented by or implemented using convolution with the associated impulse response, we can calculate our output like that. But since we have x of n, let's go ahead and substitute that in there. In particular, h of k, we have e j omega n minus k. Well, this term right here is the same as e j omega n times e negative j omega k. So using that substitution and factoring out the e j omega n from our summation, because it's not a function of k, gives us h of k e negative j omega k. And just to make the point, we've got that. Well, in this case, look at this. This is the x of n that we started with. And this, although it's a big function, notice it does not depend upon x other than it has the same frequency, omega. We can call this then. Now, really, one question is, why not h of omega? That's a good question. Some textbooks do use that notation. The textbook that we're using uses the notation you see down below, and it's fairly common. And the reason why is that it helps to visually keep track of what domain we're in. Just as we use square brackets for discrete time and parentheses to indicate arguments that are continuous in nature, kind of reinforces what's going on. Here we use h e to the j omega as a visual reminder that we are dealing with discrete time systems, and in this case what we call the frequency response of a discrete time system. When we get to continuous time systems, we'll get something analogous to that. So that's where we have this notation. So notation reserved for continuous time systems. Okay, well, now we can rewrite this one more time. This is e j omega n h e j omega. So this can be pre-computed. And it exists whenever that sum converges. So we have to worry about such things. So this is the same as stability. It turns out there are some kind of bizarre edge cases here, since we're not dealing with a general convolution, but we're actually dealing with the sum of hk times e to the negative j omega k. And those edge cases are called quasi-stable, but we won't talk about those right now. Instead, I want to put up here a great big warning. Warning. It is wrong to write y of n is equal to x of n h e to the j omega. Well, isn't that what we just had above? Yes, it is what we just had above, but that's only because we have a very special x. And if you ever find yourself writing like this, you're prone to make mistakes, and it's like bad grammar. It just sounds wrong to someone who knows their grammar. This is not what you should write. Instead, this is called mixing domains because this is generally thought of as the frequency domain. It's a function of frequency. And this is the time domain. It's a function of time. We will talk about ways to do this correctly. And we'll do that later. But first I just want to run through an example for this lecture. Okay, so say that we have, suppose that y of n is equal to x n minus 1. Very simple. We find the impulse response by letting x be the impulse, and so we can just write down h of n. So what is h of e to the j omega? The frequency response. It's the sum over all k, delta k minus 1, e raised to negative j omega k. Well, the term that we're summing is 0 everywhere except when k is equal to 1. So this is just e negative j omega. Okay. So in general, if we had a delay, if h of n were equal to delta n minus nd, for example, we would get h e j omega is equal to e minus j omega nd, and away we would go. So this is a function. When we are dealing with eigenvalues and eigenvectors, we expect it to have a value, not a function. Well, that's easy. We give it an input with a certain omega, and for x equals e j omega naught n, h e the minus j omega naught. So if we chose omega naught of, say, pi over 2, then h e j omega naught is going to be e to negative j pi over 2, which is just negative j. So it does turn out to be a single number once we've given it something. In this case, it's complex. It's the negative imaginary number, and it will always work out to some number. But we can also, because we have solved this in the general case for omega, we can show what these different values would be. So since it's complex, it gets hard to plot, so we're going to plot the magnitude. The magnitude of this is always 1 as a function of omega. That's easy. And then the angle. The angle here is going to be ranging between pi and minus pi, because if it's anywhere outside of that, we can always put it back in that general range. It'll start out at 0, and it will decrease, wrap around, and just keep decreasing like so. Okay. One other example I'd like to go through is the moving average. So in this case, we have y of n is equal to 1 over m plus 1 times the sum from 0 to m of x and minus k. In other words, we are just summing up m plus 1 samples and dividing by m. So h of n is going to be 1 over m plus 1, sum over the same range, delta n minus k. And h, e to the j omega, is now, you can pull that out front, we're going to have two sums, minus infinity to infinity of our h, which looks like this, delta L minus k, e the minus j omega L. Well, this is going to be 0 everywhere except, well, where L is equal to k. Keep our thing out front. So we can just do the sum over k. All the extra L's don't matter. And this is going to be e minus j omega k. Now what? Well, fortunately, if we have a sum of some value raised to a power, that's equal to 1 minus that quantity raised to m plus 1, a value 1 greater than the highest power summed, over 1 minus the quantity that's raised to the power. So there we go. That may not be more insightful than what we just had, but we can factor values out of the top and the bottom of this, and out of the top we're going to factor e negative j m plus 1 over 2, and out of the bottom we'll factor e negative j, oh, there's an omega there, omega over 2. Then that gives us e j omega m plus 1 over 2 minus e negative j omega m plus 1 over 2 all over e j omega over 2 minus e negative j omega over 2. When we have the difference of complex exponentials with opposite signs in the exponent, we can resolve that using the formula that we've seen previously, Euler's identity, and we have a sine function here. So this comes out to be 1 over m plus 1, and we can simplify our factor out front to be m omega over 2, or omega times m over 2, whatever you prefer. And then by adding a 2j up here and a 2j down there, we don't change anything. But now this is equal to a cosine, or a sine rather, and this is equal to a sine, giving us sine of omega m plus 1 over 2 over sine omega over 2. And this is called a Dirichlet function. So I have added a MATLAB plot of this particular function for m equals 5 over here to the left, and you can see the code below. So next time we'll talk about applying frequency response concepts to signals in general. Thank you.